Okay, welcome all to this sixth lecture of the Continual Learning on Machines that Can Learn Continually course offered at the University of Pisa in conjunction with ContinualAI and the AI Doctoral Academy. In this lecture, we're going to talk about methodologies. Again, as the past lecture, we're going to focus on these aspects of learning machines, but today we're going to delve a bit more into two different, let's say, categories of algorithms, the regularization ones and the architectural ones. And then, of course, we will conclude the lecture, as always, with an hands-on session with Avalanche. Okay, before starting, let me ask if you have some questions related to the previous topics covered in this course. Maybe some issues that you encounter, or just if you want to comment or something, if you want to ask a curiosity or something like that. That's even something that we can discuss at this point. Okay, that's great. So please remind that I'm always available to you guys and girls via my official emails at vincenzo.lomonaco@unip.it. So in case you have any issues or you want to discuss something, well, just get in touch. Okay, so the lecture is going to be split in three different parts. As I mentioned, the first part is going to be about regularization strategies. The second part about the architectural ones, and the third part will be about Avalanche. I also reserved a bit of time to play a bit with Avalanche with you guys. And so if you have the laptop here available, we can start together, maybe a notebook, and you can do it live with me. And I can have also Andrea here and remotely also Antonio, I guess, helping you out in case you have any trouble. And so let's see how it goes if we have the time to go through it. Otherwise, that would be an interesting exercise for you to continue at home. Okay, so regularization strategies. We started our investigation about possible methodologies, possible algorithms, or better strategies that you can use based on replay last time, if you recall. And we said that replay is quite of an effective and general approach to learning continually, while it's difficult to ground it in let's say, a more biological inspired approach to learning continually. And I think it is worth investigating different approaches to continual learning that may be more efficient and I guess more in line with this kind of a neuroscience grounded view of continual learning, even though, as you may imagine, this is the only possible view of continual learning. And we're going to discuss about alternative views of continual learning, maybe also considering for example, distributed computing and other, say, research area in the context of computer science that depart significantly from the main assumptions of biology. But regularization strategies per se, I think, are particularly interesting because they get to the core issues of learning continually. That would be just by looking at the current data that we have available and building a more, complex representation of the world incrementally over time, and possibly building these robust, high-dimensional, hierarchical representations in deep learning, directly starting from non-ID data. And so in terms of the history of development of strategies in this area, of course, looking into the deep learning literature, I think we can first discuss about an important and seminal work. These papers are linked at the bottom of this slide, an empirical investigation of a catastrophic forgetting in gradient-based neural networks by Goodfellow et al. Goodfellow, one of the main authors of the deep learning book, as you may recall, that really sparked a lot of interest in catastrophic forgetting and continual learning in 2015. And was mostly based on an investigation of how different, let's say, training regimes and strategies and basic, let's say, optimization algorithm may impact on our ability to learn continually and generalize over time. And so we are talking about basics, let's say, adjustments that you can make to the core SGD algorithm so that you're more or less prone to forgetting. For example, at the time was more investigated the idea of early stopping. So this idea did not push too much learning on the current task and the current data you have available, and to avoid somehow overfitting to this small amount of new data. Or just enforcing like well-known regularization terms that we already studied and appreciated in the literature, like L1 and 2 regularizations and dropout, for example, was proposed by Hinton a few years before that. And in fact, they can be proved to be linked to better generalization capabilities and hence less subject to forgetting itself. So we don't have the time to look at all the different, let's say, directions of explorations in this particular, let's say, area of research, but it is worth considering that, let's say, these approaches and methods were, let's say, early explorations that would indeed impact on our ability to learn continually, but were not enough, let's say, to generalize to more complex scenarios where these forgetting issue, like in class incremental learning, is really preponderant, and it's difficult to tame it just by fine-tuning, let's say, these basic regularization parameters that we often use in deep learning. So a more recent work that was published by Mirza et al. In 2020, Understanding the Role of Training Regimes in Continual Learning, is another interesting paper that is, let's say, more recent and somehow closes the loop, let's say, with respect to these kind of investigations that for some time were like a bit, let's say, intended as some, let's say, vague, straightforward approach to control forgetting, but now they are considered again as important aspects that you need to take into account when you develop a new continual learning strategy. So you shouldn't try to focus only, let's say, on new interesting ideas and approaches to continual learning, but you also look into the real basics of it, right? And try to understand how the optimization process is impacting learning continually. And these are the few interesting pointers that I imagine you can investigate first. For example, I don't know, you have to choose at some point what is going to be your learning rate, the dimension of your mini batch, and you know, how many iterations you want to do on a small you know, amount of data you have available, and so on and so forth. So in this image on the right, I think it's quite explicable. On the second paper I was mentioning, you see these different curves, accuracy curves over time, show that with the same network and the same exact protocol, let's say, then you get very different results depending on this set of hyperparameters that you can set, like dropout, the dimension of the mini batch size, the learning rate decay, and and so that say pose some interesting questions, right, on what we are doing in continual learning. So it's not just finding the best parameters that we select, as we also explored in the lecture about evaluation protocols for solving a specific task at hand, but it is also about the overall ability to generalize and to learn continually. And so in this strategy, for example, the blue one, the overall accuracy is decaying with a lower piece, I would say. And the only downside of this is that you can learn just a little worse the current task at hand. So you're sacrificing a bit of performance on the current task you're solving. So you're not going to a full convergence of that task in favor of not forgetting the previous tasks you encounter, right? So it's always a trade-off, an important trade-off. And this also helps me to, let's say, stress to you guys the fact that you need to control not only forgetting, but the overall metrics you're interested about over the overall stream of data, not just the current experience and the current task. Okay, but yeah, these are the most basic thing that you would, I think, start to work on when you try to improve your performance on a continual learning agent, right? And in fact, this is also part of my personal experience, right? In 2016, I was working on continual learning strategies to let's say, improve the ability of a convolutional neural network to learn over time. And so this particular experiment that I wanted to show you here, also to motivate your own enterprise into this area, is mostly based to the Big Brother, you know, the TV show. I'm sure you know that it seems it is useful for some reasons, right? And in this case, so these I think it's 7 different subjects were recorded for the entire, let's say, season, right? Because they were finalists in this TV show in which you have to stay, you know, within this house for more than a month. And so it's interesting that this data set provided us the ability to, let's say, have a possibility to have a benchmark in which we wanted to improve the ability to recognize these different phases over time. And we would expect our system to improve its ability to recognize these different persons over time as they are more and more data related to these persons are more and more available to us over time. And so in this case, so these finalists were present in the house for more than 50 days. So this is the number of experiences that you get in our experiment. And we used this Violet-Jones classic, let's say, algorithm, computer vision algorithm to detect phases directly. So the task here was just start from these segmented, let's say, phases. You can see an example of down below. And the idea was to find the best way with convolutional networks to detect these phases. And in this case, the approach that was proposed was indeed based on this idea of an adjustable learning rate that was tuned based on the data availability over time. And you can see on the right here that these different accuracy curves are related to different choices of the hyperparameters. And if you have an adjustable learning rate, the blue curve here, you can maintain a quite let's say, important performance in terms of the ability to recognize these persons over time, and you can actually improve them a little at the end of this entire, let's say, exposure to 55 different experiences of a short amount of data available each day. So, and a number of different strategies, approaches, let's say similar to this one has been proposed over time. And I invite you to check out the references of those papers if you want to explore more in this area. But that you need to know that in terms of regularization approaches, there's a lot of space to explore how even basic algorithms in optimization should be better, let's say, understood in the context of continual learning. Then if we had to move instead to one of the, I would say, commonly used reference strategy for continual learning that can be considered as based on regularization, we would definitely need to go through learning without forgetting. Learning without forgetting, you know, apart from these very suggestive and interesting names that were chosen, is one of the few strategies I think that was actually published also on PAMI as an original strategy to continual learning. PAMI is, of course, one of the most, I would say, prestigious journals that we have on pattern recognition and computer vision. And it was something that was proposed before, I think, the original paper is before 2017. And it goes by the name Learning Without Forgetting. If you want to explore it, I suggest you to read it. It's quite interesting and powerful. And it's all based on distillation. So how many of you here, just as a curiosity, are familiar with the concept of knowledge distillation in deep learning? A few of you, that's great. But just for the sake of clarity, knowledge distillation was something that was proposed in 2015, I think, by Hinton, Turing Award, and others. In this paper, distilling the knowledge in our network, it is a methodology, a quite simple but powerful methodology that allows you to distill the knowledge of a pre-trained network into another network. So essentially what you do in this approach is to start with this pre-trained model that you have already and the data that you have trained this model on, right? The training data related to the task you want to solve. And then you try to distill the knowledge from this model to another network topology, in general, a smaller one that will be more efficient, right? And so the idea is that instead of using just the training examples and the labels, you want to use the training examples and the targets that are computed from the pre-trained network. And these targets are, in general, much more informative than a one-hot encoding, for example. And that's quite also intuitive, right? Because you have much more knowledge about the connection between different examples. So an example, for example, in an object recognition problem, maybe a dog, for example, the target for this dog picture is just one for the class related to the dog, one-hot encoding format, and 0 for all the other tasks. But this example may be, this dog in particular, may be very similar to other classes of dogs or even cats or other animals, right? They have quite a lot of interesting features set that they share. And so through this, let's say, a step of computing the targets, the probabilities belonging to the different tasks, classes we consider, we can have a much more informative targets that we can use for distillation. So in the end, for training the smaller network, the other networks starting from scratch, we can use the actual training examples and the targets computed in this way, and we can converge much quicker and even get to better generalization capabilities. So that's great. And it's quite a simple strategy to implement, and was here the very basic of learning without forgetting. So in learning without forgetting, the main idea is that as we move from one experience to the other, we want to maintain the model just computed at the previous step, the previous experience, and just to apply naively distillation here, we would need to have access also to the data belonging to the previous experiences. But this is something that we cannot have, right, in continual learning. So what we do as an approximation is to use the current data to get the targets from the previously computed model and to the distillation with these targets. There aren't any particular guarantees that this will be successful. So that's bad news. But at the same time, in terms of practical application, learning without forgetting has been shown to be quite effective. And this is often because the example related to these different experiences are most of the times quite connected. They are belonging to similar distributions. So this approximation may be effective in practice, but may depend on the problem we are solving. Okay, so this is the main concept of learning without forgetting. And here in this image on the right that was taken by the original paper, you can see how that can be related to different approaches: original model, fine-tuning, joint training, feature extraction, and the actual strategy, especially considering the simple task incremental setting that we discussed in the previous lectures about benchmark and scenarios. And that was, if you recall, one of the main drive for continual learning in the early days, let's say, of deep continual learning. So that's essentially a scenario this particular strategy was tackling with a multi-head, if you recall, implementations here at the end. So you encounter different experiences, and for each experience you have a different task, and you operate this distillation approach every time a new task is encountered, new data are available. And so the idea again is here to compute these targets every time with the new data, and to try to add different losses so that the predictions essentially for this task are as stable as possible. So they're not changing so much, even though you're changing the weights related to this particular model over time to suit the new data. Okay, I don't think it is worth going through the description of these different approaches we already described: this joint training, fine-tuning, and this idea of freezing all the model and using it just as a feature extractor. But that's something you can explore maybe at home. Okay, what's nice about learning without forgetting is it's super easy to implement. We're gonna see the implementation more in details, I guess, in the last part of the lecture. So don't worry if you don't get everything already right now. I didn't put the actual equations, but in the end, it's just adding a couple of regularization losses so that the predictions that were made as the first initial step in the training of the current experience can be maintained as they are, as they were. And this nice thing about the learning without forgetting is not just that it's easy to implement, but also it's quite generally applicable, even with single ad implementations, and for scenarios in which maybe you don't have the task labels as it was first proposed here. And as you may imagine, the knowledge distillation is one of the core, I would say, technologies that we can use with continual learning. You will see like a very commonplace, and so it's something that you need really to look more in depth. Okay. And yes, I also mentioned here our paper, Continuous Learning and Synchronous Mental Task, as in this paper, we list, let's say, all these different basic strategies that were proposed in the past, and we try to see them well described in the paper in terms of both mathematics and implementation aspects. And so I suggest you to read through this paper if you're interested. It's very more, I'll say it's more of a didactic paper. Most of the times you see all these different papers that have been published at top conferences or with very short space. So you don't have the space actually to specify all the different tricks, implementation aspects, and other interesting things that if you really want to understand them through, you instead should be able to, you should investigate and be aware of. Okay, and now let's move to another, I would say, seminal work. I think it amassed more than 2,000 citations already from 2017. It is quite of an important paper to know, and so it's Overcoming Catastrophic Forgetting in Neural Networks, published in 2017 by Kirkpatrick et al. From DeepMind folks. And essentially, it's quite interesting. I think it was one of the first, let's say, papers that were really taking into consideration a more neuroscience grounded, at least, approach, where at least the choices of this approach were argumented through, let's say, more advanced memory consolidation theories or neuroscience theories. So it's nice to read it through. There's also one of the co-authors is Claudia Clopa, that is a well-known researcher at the Imperial College working on synaptic plasticity. And so I think that this paper is quite interesting and worth reading through if you're following this course. And one other thing that I want to mention, maybe I should have put the link here, but the main ideas related to this approach, even though this was indeed quite an interesting further developments, were proposed originally, I think, in 2013. By the algorithm HELA that was proposed by Eric Eaton et al. And the main ideas, let's say, related to this EWC, elastic way consolidation approach, were already proposed in that paper. I think it was the main reference of this paper. But then again, this was let's say, the first formulation within deep learning, I would say, with deeper networks, and also considering reinforcement learning experiments. And by the way, I want also to clarify that all the things that we have discussed in this course up to now, they really apply very well also to different paradigms like reinforcement learning as well. So even though I'm focusing on my didactic material and explanations on more of a standard supervised learning setting, you need to consider that many of these approaches and these ideas are quite also usable in other paradigms like reinforcement learning if you're interested in those. So coming back to elastic way consolidation, if you recall, this was the picture that I first introduced in the first lecture, I guess, to describe how an optimal solution in terms of the same parameters to solve different tasks may be found in some cases, but if you just apply like basic regularization strategies and approaches, we may end up in a spot in which of the optimization landscape in which we are not able to minimize either of those losses, right? So this picture was taken indeed from the AWC paper, where they motivated essentially the proposed approach to find somehow a nice trajectory and correct, let's say, this trajectory that would naturally flow into this green or green arrow, right? If you try to optimize only on the new task, let's say the B task, where you have this first gray area that is the A task, and instead correct this trajectory to follow this path instead, hopefully. And so the main idea here is to just rewrite the loss as follows. So the loss, over the parameters of our model can be indeed computed based on the loss, for example, like entropy loss, the loss that would help you optimize for the task B, plus a regularization term, right? That essentially is going through all the different weights I of a particular model, and is essentially disincentivize the change in the weights that are important for the previous data distributions, the previous task, in this case A. How we can do that in math, right? So the idea is that if we can have these metrics, or let's say importance value for each of the weight, so Fi is the importance, let's say that we have this notion of importance for each weight I, then if you multiply this by this difference, that is essentially saying the current weight theta I, as we are optimizing it right now on the current task, how far it is moving from the optimal weight computed for the task A. So this weight, that is A I star, is the optimal weight computed just at the end of the first task A. So we know that it's the optimal weight, right, for that particular task, for solving that particular task. Then what we want to disincentivate is to actually change it, and this is the difference, right? So we are computing how far we are moving with respect to this particular weight. So we would like to not change it, especially if the weight is particularly important. So we have this elastic way of changing these different parameters into our model so that the weights that are important are less changed than the weights that are less important. So there is, of course, a main assumption here that the importance of the weights in a particular model are different. So there are weights that are quite important and weights that can be actually changed without any much concern. And you can say that if you have some experience in a pruning algorithms or something like that, you may, I don't know the exact percentage, but like an incredible amount of weights can be pruned without hindering too much the accuracy of a model. So this suggests that some weights are much more important than others. And if you look at the distribution of the importance, I don't have here a picture, but there is quite of a power law, let's say, plot that you can drive. So if you decide that you want to preserve just a few of those weights, if you had to put a threshold, let's say just a few percentage of those are really important, and the rest can be rewritten or changed. So this means that there is a lot of space within the same model capacity to house different tasks and learning from different experiences over time, and that we can apply strategies, regularization strategies like elastic weight consolidation to let the, let's say, the optimizer find the best way to change those. Is this clear, or do we have some questions?
The I, the importance, okay, is a parameter of the learning. I mean, the importance is changes during learning.
This is an interesting question, and so in the original proposal here, the importance. In the original proposal, the importance was computed based on the feature information. So this is something that you can use to compute the importance of a particular weight, especially considering it as a more of a, I would say, probabilistic model. But then we have different alternative implementations to actually compute the importance of each weight, and they all can be plugged, let's say, into this particular formulation. Indeed, many different variations starting from WC are based on this idea. So leaving intact the main, let's say, regularization term as you can see it on the slide, and find different ways, maybe more efficient, to compute the importance. So a basic approximation that we also implemented in Avalanche is to compute the feature information approximated as the variance of a particular weight on a few samples that you can extract from the actual training set. So we don't have the time to go through the math of it, but if you look at this paper, there are some interesting hints, and there are also a couple of papers in which there's quite of an argument also going on how this should be implemented and how that can be approximated rather. But yes, I discussed this several times also with one of the authors, Pascano, that essentially was saying that for this particular paper, they use instead the actual feature information that is computed is quite computationally intensive, but is more accurate. And I guess for instead longer sequences of experiences and for a good computational accuracy trade-off, first order approximation of the feature information is the way to go. And there's another important limitation of the main approach here. So if you look carefully, so here we are modeling just the switch from task A to task B. So what happens if we have not just two tasks, but a number of them? So if you had to follow this implementation, we not only we had to compute the importance at the end of each task with this procedure, but we also need to add additional regularization loss for each of the tasks, each of the experience that we encounter. And that would be okay, but the problem is that for each of those regularization terms, we need to add both the optimal weights computed at the end of the task. So it's like a snapshot of the model. Entire snapshot of the entire model may be very big, right? In some cases, plus another snapshot essentially of the model that is essentially the importance value, the general real value that is computing the importance at that particular point in time. So if you really had to maintain this basic formulation, you would need quite of a big space and also some overhead in terms of computation. But there are the nice news here is that there are different online, let's say, approximation that have been proposed, like online WC. No, there is no paper about that. But if you look at the progress and compress strategy that we're going to discuss in the next lecture, that is a more of an hybrid strategy. Then there is also a formulation there that is optimizing WC so that you, in the end, maintain just the optimal weights, the last weights they computed the step before, one snapshot, and one snapshot that is the, let's say, unimportance value for each weight that you carry on and you approximate over time. So that's quite useful because we end up in that's the desiderata that we discussed before, in which we have bounded, let's say, computation and memory resources that do not grow linearly, at least with respect to the number of experiences we encounter over time. Okay, so this was an important seminal work that you can maybe investigate more looking through the paper. And I guess if you work in this area, you're going to encounter several times, and it's worth, let's say, study more in depth. Okay, then an interesting, let's say, way of computing instead the importance value, as we discussed, was proposed instead in this synaptic intelligence approach. The paper Continual Learning through Synaptic Intelligence by Zheng et al. In 2017 was indeed a possible different, I think, even more elegant approach to compute the importance of a particular weight. And then you would use, again, as we discussed previously, the same kind of formulation to regularize learning on the new data. So here, the idea is that, the main idea is can be rewritten instead of this math here, ugly math on the right. You can summarize it in this sentence. So the importance of a parameter may be seen as proportional to its contribution to the loss decrease over time. Now that's quite reasonable, right? It's intuitive. So we can say that if that parameter has contributed very much in its change, of course, to the decrease in the loss, that means that that parameter is probably very important for the task at the end, right? And so based on this simple idea, well, here is more of a motivation on the right why this is the case. We can go through it, But based on this idea, you can create like efficient online implementations to compute the importance of a particular weight. And what's nice is that you have this approximation even over time. So you don't, with the WC, at least for the initial proposal, you had to compute the importance at the end of the train, so at convergence. In this case, you can approximate at any point in time the importance of particular weight because you are updating that over time. You're incrementally building it. So that's quite interesting. It's very efficient. And what I have found to be difficult, but also with WC in general, with regularization approach, it's difficult to find a proper hyperparameterization that would work well on different data and different scenarios, different streams of experiences. So that's, I think, one of the downsides of the current approach is quite sensible to the hyperparameterization. Okay, so if we look here instead to the main motivations, so the paper follows the description of this approach, just starting by this idea that, well, you can see the change in the loss given a particular, over time as approximated, let's say, as following the definition of a gradient, as the sum over all the weights, in this case, the index here is k, of the gradient k, step t, times this instead term that would be the change of that parameter k in time. And so, so this is a snapshot in time. So if we are essentially considering loss a particular time, and we see a particular delta in time, then we can compute, let's say, we can see that the difference in the loss, possibly a decrease in the loss, as we said before, over time, may be rewritten in as this multiplication, right? Then, if we had to consider a particular window in time, right? So, for example, moving in this case from task 0 to task 1, then we can say that this decrease in the loss may amount to this integral from t0 to t1 of this product, right? So what we've written here, and so. So in the end, what we can write down is essentially this, right? So we can say that what we said before would be an interesting estimate of the importance of a parameter. We would just this essentially running sum, because this is the integral. Well, if you're considering just one parameter k, then it's just 1k. But if you're considering overall the loss, the contribution to the loss is the summation of this product, that is the gradient times the weight update. So in the end, what's nice is that we can compute what's interesting for us, that is this omega k nu, that is the importance of that particular k parameter, in this case for this trajectory of learning a new task nu. Starting from the previous task nu -1. So this is the importance that we're interested about. So it's quite easy to approximate just the product between two things that we already computed for the gradient update, and then we can use here this omega, small omega, to compute this big omega. That essentially is this small omega with some additional hyperparameters we don't have time to go through, but just to stabilize a bit the whole thing here. But essentially, once you have this importance value for the task nu, then, well, you can plug it in, as we already seen in the previous formulation for AWC. Okay, and that's it. So this was the formulation proposed by Zhang et al. I think we have this in Avalanche as well, right? Implemented, so you can look also the code if you want to know how this can be implemented in code. So then these were like important strategies that we couldn't not talk about in our course, but then I think that it's quite interesting to look a couple more of those regularization strategies that For example, in this case of hypernetworks are quite, I think, original and diverse with respect to what we have seen before. So in this case, this paper was published in 2020, Continual Learning with Hypernetworks. The main idea is to instead of trying to regularize directly a particular mapping function, a particular parametric model, the idea here is to have a network that on demand can generate the parameters of a network that can be used to solve the task at hand. So there is, it can be seen also as a meta-learning approach somehow, but somehow the idea here is to have a more, let's say, abstract model that is able to generate, let's say, child models on the fly to solve a particular task. And so you may ask at this point, so, okay, but what's really the point of this, right? So we would forgetting in the parent network. So we are not really solving the main continual learning issue here, right? The main assumption here is that if you work into this, let's say, more compressed, higher level representation space of the whole, let's say, functions that you can generate to solve different tasks, and in this particular space, forgetting is less of an issue, and continual learning is easier. And this is the main argument that somehow this paper is trying to convince you about, and there are some evidence in the paper that suggests this may be the case. Problem is, of course, is as many of those approaches that are quite difficult to scale on higher dimensional problems. So if you're looking at applications with high-dimensional patterns like big images or more complex tasks, even without task labels, that becomes quite difficult. But yes, just to look more into this main schematic representation of the approach, here these letters here are not the experiences, like, so don't get fooled. These are embeddings that essentially are trained so that based on those embeddings that represent somehow the task at hand, you can really decide what kind of parameters to generate to better solve the specific task at hand. So you're generating these target omega parameters so that you're able to handle with these target functions, you generate these particular X values and predict the correct output. Okay, so this may be an interesting approach but again, I think that a bit more of an exploration in terms of its scalabilities would be needed, and it needs somehow, and at least in this original formulation, even though in the paper they talk about different ways to avoid using these additional supervised signals, maybe quite interesting to explore how to improve that on that line of work. Then here on the right there is also an interesting point added by the same authors. The idea is that you can actually even compress even more an hypernetwork based on this chunked approach, where you generate iteratively the layers of the different target networks. But yes, you can take a look at the original paper if you want to learn more. Okay, so if we had to try to conclude something about the different regularization strategies in continual learning and like a trajectory of development for them, I think we can start by saying that well, at least what I believe, they are quite elegant in terms of formulation. So it seems to be like one of the few approaches in continual learning that look a bit less of an heuristic or of a patch to an existing system, and are more, let's say, developed towards this idea of a principled algorithm to solve continual learning. And so I see them as like a way to break through, this particular path of continual learning, and to look at more, principled algorithms, especially optimization algorithms, right? That could bring us closer to this ability to learn continually, and not just find patches, architectural or replay or other strategies that can be seen more of a engineering, let's say, solutions. Then we know. I think. Different researchers may think differently, but I think that is quite more evident that regularization approaches work well with domain incremental settings and less well with other, let's say, settings in which there is a lot of forgetting imposed by the very nature of the structure of the task, like class incremental setting. I think that for the future of these area, better investigation of the inner gradient dynamics would really shed some light on future interesting research venues. And also that it would be interesting to maybe understand better how different orthogonal regularization terms they play out together, right, to improve our overall ability to learn continually. As they can be seen as a plug-in system, right? You can adjust different regularization terms to your loss, and that mostly define a regularization approach. And so what I expect for the future are significant advances in this area in the years to come, even though it appears now to be something that is not really at the epicenter of the current focus on continual learning algorithms development today. Okay, so let's now go through the different architectural strategies and approaches, at least a handful of those, just some that approaches that I think you should really know and maybe explicative for other interesting approaches. Of course, I'm sorry for the different authors of very interesting approaches that maybe are seeing this course, and I couldn't talk about them all. But I think that maybe I can say these informally right now. It's quite an announcement. So we probably have continual learning full-blown course, the master's degree level, here at the University of Pisa next year. So that will be a chance to really go through all these different approaches in 40 hours of lectures that we will host. So that will be quite an important step, I think, in this research area. And we're really proud to push this endeavor forward as one of the first universities that will offer a graduate student, let's say, a course in this area. So coming back to our formulations here and the architectural strategies. So we already discussed in the previous lecture about the multi-ed architectures. Implementation that would nicely fit into a task incremental setting where we have the availability of these task labels over time. And so the main idea again here is to specialize the behaviors of a particular agent or our parametric model with additional parameters that are custom, let's say, and can be used specifically to solve that particular task or to model that particular sub-distribution. And so what's nice about this basic approach, so in the end, just adding a few task-specific layers that can be used on purpose, is that there is a clear separation between the shared set of parameters, these shared layers here, so things that we know shared among these different tasks. For example, feature extraction, different visual cues that are common with respect to the classification of these different objects, animals, etc. And then private parameters that can specialize and customize and change maybe this basic understanding of the world, depending on the specific task needs. And so we mentioned that the perfect situation here is, of course, to have the task labels at play here. And so we get access to these task labels during training and even during inference. So I am an agent, I'm moving around, and now I'm set by some teacher, some master, please pick up that particular object. So that's a direct task, right? And so the agent can specify its behaviors to go to that particular room and pick that object. And again, if I ask her to collect another object, the agent can respond accordingly. So that's okay, I mean, in some cases, but the problem being that many, as we discussed in the benchmarks lecture, sometimes this is a bit forced. You know, it's a bit, a constraint that is enforced, not because of application, let's say, necessities, but mostly to help out the continual learning algorithm agent to work with these even simpler architectural approaches like the multi-ad implementation. And so what I want to stress here is that we don't actually need necessarily this task label, task information to operate with architectural strategies. So there are many papers and many ways in which we can come up with a different, let's say, notion, I always say an internal, let's say, notion of a task, so that if we deem that it's important maybe for this particular sub-distribution is very different from what they've seen so far to be modeled as a different ad, then I can definitely do it without the explicit external notion of a task. Another naive, I would say, approach would be to just have a new ad for every new experience that you have, right? So you can just create a new ad, and then these ads are competing, let's say, to in inference, especially to decide what to do, what are the actions, for example, that particular agent picking objects, right? So that's interesting, but if you have very small and frequent, let's say, experiences available to you, like hundreds, thousands of experiences over time, then this approach quickly becomes rather ineffective, pragmatically. So another strategy that we actually proposed when I was still at the University of Pisa is what's called the copy weights with Rainit approach, and it's an approach that may fall also in that alternative categorization we discussed in the last lecture about parameter is isolation methods. Right? Try to isolate some parameters so that you preserve that knowledge and you can reuse it later. And so this approach was initially developed in 2017, but was later refined in this latest paper, Reaction-Free Continual Learning over Small and Batches, where the focus was really to try to find out architectural strategies that would work efficiently with this very small set of experiences, like 300 images, like almost online. And without any notion of replay, so without any replay. So how you can do that? And so we improved the study strategy, summarized with these CWR letters and star, that is like the latest implementation that we proposed. So yeah, maybe before looking at the pseudocode, I want to say that this is mostly is a very simple approach, quite easy to implement. This is mostly based on the final, let's say, fully connected linear classifier on top of a particular neural network. So we try to address that, as we empirically found that for many interesting continual learning problems, you may start from a pre-trained model, and pretty much the forgetting happens in the last layer. And so in some practical cases, it may be interesting to just isolate the notion of learning a robust representation, but the fact of learning different classes and concepts over time. So this approach is mostly based on a dual memory system, where the basic idea, also a bit of loosely inspired by this hippocampus neocortex duality, the idea is to have a memory that is very much plastic. It is able to learn fast and change things rapidly, and then instead a consolidated memory that is instead for storing long-term representation which you would reuse. And the nice thing about the CWR is that it is very agnostic with respect to the experience content. So regardless of the fact that you don't need task labels in this case, then you can have new examples related to classes we already seen. You may have completely new examples related to new classes you had never seen before. Class incremental settings, for example. You may have both of them. You may have big or small experiences. This strategy would work well, nevertheless. And here is the definition of the main strategies as a pseudocode that you can see. And we have essentially two different memories, let's say. You can see them as like a dictionary of weights related to a particular, let's say, neuron, output neuron, right? So we have the consolidated memory, CW, so these weights are consolidated, and then we have TW, there are these temporal weights for this temporal memory. So the idea is that for each training batch, it is for each training experience that we encounter over time, what we can do is to say, okay, let's reinitialize our fully connected layer with 0. So this 0 init is quite fundamental. So if you need to with a different random values, this may evenly impact on the amount of forgetting. And this was well explained in the paper. But yes, if you 0 init the classifier and you copy into the temporal memory, let's say the weights related to the actual model that is able to learn from the current experience data, all the weights that of the classes that we already encountered in the past. So you want to reuse that knowledge if you have that. You can start by training your model with SGD, and then when you finish, let's say, this process, you may start to look at how to consolidate back this knowledge into the consolidated memory CW. And so, the idea here is quite simple. You may want to have, let's say, an average, a reasonable average over time of those, let's say, value that you have for each of those weights, considering, of course, the amount of time you have seen the same patterns again, of the same classes again and again in the past. So if you've seen them a lot of times, that it's reasonable to assume that you don't want to change them so much as you would do with things that you have never seen before. So you are saying, well, in my, let's say, average of the best value for this weight, I want to take more into account the past and the previous consolidated weight, if you encountered that multiple times, with respect to just a weight that you have never encountered before, where you say, okay, I want this latest version of knowledge with respect to this particular weight to be favored in this case. So this is essentially consolidated step, a very simple, let's say, normalization average is based on this idea of W past J, so the number of times you are seeing that particular class in this current batch called J with respect to the past, essentially. And so you accumulate into this past the number of times you're seeing that particular class J. And of course, in case you're interested, you can look maybe more carefully at home these pseudocodes, but it's quite simple and I think intuitive. Any questions so far while I take a sip of coffee? Okay, that's great. So in terms of other important, not to miss strategies, architectural strategies that are being proposed, then I think that progressive neural networks is a strategy that cannot be missed and was proposed in 2016 by Russo et al. And essentially it is, I would say, a pure architectural strategy that essentially tries to expand the main model topology to house, let's say, new knowledge over time by leveraging what you have previously learned, mostly through forward transfer, this notion we have seen before. So things that you learned in the past may help in learning new tasks and new things. So the basic idea is quite straightforward. So the idea is that you have a particular model, for example, a CNN here, feed-forward network with different layers from 1 to, well, in this case, just 2 layers, but n layers and the output, right? So this is called in this method a column. So a column, maybe also recalling that it is the column in computation neuroscience, like one of the building blocks of many computation neuroscience models. It's a cortical column. And the idea is that as you move to another experience, then you may instantiate a completely different column, so a replica of this neural network, that instead of just being trained completely alone on the new task data, contains also some interesting lateral connections with different columns. And so the idea is that, for example, if we have this particular, let's say block, let's say this block H2, 3, then this block is connected with all the previous blocks of the previous cortical columns and the precedent layer in the network. So what we are saying is that this representation, right, at the end of this computation of H2 can take into account not only what has been learned in a hierarchical representation learning scheme from each one, but they also leverage these different representations that have been, let's say, created and extrapolated based on the notion of solving these different tasks 1 and 2. Right, so it's reasonable to say, and if I'm, let's say, playing different Atari games over time, and so in this layer, what I may see, for example, the first layer is how to represent, best represent, compress, let's say, the knowledge of the edges in the Atari screen, right? So this knowledge is reasonable that is going to be useful to represent also something more abstract, for example, a ball or some object in this screen of this particular task tree. And so we have quite an interesting way of knowledge forward through architectural changes here. And here is the formula. It seems more complicated than what actually is, but it's just saying that a particular activation function f is computed on the dot product of the actual weights and the activations on a particular layer I minus 1, so this 1%, for example, and as well a sum over all the different columns that are preceding the current column as a multiplication between their own representations I minus 1 of j, that is these previous columns, and additional weight mask, so these different connections, and plus they also propose this kind of an adapter approach, so that these essential representation weights do not grow massively with respect to the number of columns that are introduced. So you can put here like a dimensionality reduction layer. For example, in convolutional neural networks, made a one-on-one convolution that is reducing the number of future maps that you add over time. Or for a simple fully connected model, maybe just a fully connected layer that is reducing the dimensionality of the neurons. But nevertheless, this adapter can be also trained and to see how to better combine this different knowledge. So this is quite interesting in terms of architectural approach, but the main problem is that, as you may imagine, is quite important in terms of overhead, in terms of memory computation, as we are creating a replica of a neural network for each experience. This is quickly becomes impossible when you have hundreds of experiences, at least with current technology and models we are handling today, in vision, for example. But this idea of adapters and pruning pruning maybe these connections may be interesting, and there are many advanced more of architectural strategies that are based on this main concept and are trying to change the modularity and compositionality of this particular approach to remove the particular let's say computational and memory complexity, but also to reduce the need of different task labels that you may imagine is something that was initially proposed to be available in this model formulation. Okay, so there are a couple more interesting approaches to architectural strategies. One of those approaches being masking the weights. So one basic approach that was proposed initially by PACnet and maybe later refined in piggyback papers from the same author and colleagues around 2018 was this idea of starting from essentially a pre-trained model that is called a backbone, and then finding masks to change the model behavior to suit a particular task. So instead of creating new layers, new parameters, why instead don't we leverage that idea that we mentioned before, that, from a set of weights, you can do many wonderful set of things. And so we can change how the model responds to a particular pattern, how the model creates these different hierarchical representations just by tweaking particular, let's say, usage of a particular set of weights. So you may find different masks that are able to do this based on a pre-trained network, a model backbone. And what turns out is that this is incredibly efficient in terms of computation, because it's just a mask applied to the weights, and in terms of memory, because a mask, especially if you do this binarization step, so you train the mask with real value, so you understand the contribution of each of those different weights, but then, and you change the mask with gradient descent, but then you essentially put at zero the weights that are not so important based on a particular threshold, and you put to 1 the weights that should be used instead. Then you can compress this mask with very few bits, right? So in the end, with an handful of kilobytes, maybe, you can have a different mask for each of the tasks that you're trying to solve. And the nice thing here is that you can achieve zero forgetting, essentially, because if you maintain this mask into memory, if you don't change the weights of the backbone network, then you don't have forgetting at all. And so this approach, in terms of practical application, I think it's quite useful and interesting. One of the few approaches that guarantees you zero forgetting, right? But the problem here is that it's quite difficult to do forward transfer of knowledge. Well, we didn't mention this before, but the main problem is that even though it's there forward transfer, there's no backward transfer with progressive neural networks, so you cannot change. This part of the network is frozen. The same here, the backbone is frozen, the masks somehow start from scratch every time, so there's no real notion of forward transfer here, built over time at least. But this is a major constraint. And then you will need a different way to understand what kind of task you're solving, because based on those task notion, you may choose the best mask accordingly, right? And so even in this case, it's not clear how much it is possible to use these kind of architectural strategies based on the task definition to generalize on situations which maybe you have thousands of different experiences, or maybe an online fashion in which you would need to create a different mask for every pattern you encounter. That's quite difficult to understand how it would be extended. And then another interesting different idea would be, instead of masking the weights, would be to instead mask somehow the activations, like the neurons in themselves. And this is quite a powerful idea, because mask on the weights may be quite big in terms of dimensions, while the masks on the activations are mostly order of magnitude less in terms of quantity than the others. So it may be quite useful to look at different approaches to mask the neurons instead. And it's not, at least to me, it's not really clear what of the two strategies would be better in terms of performance metrics. But essentially, in this paper, our attention to the task overcoming catastrophic forgetting with our attention to the task. The main idea is what you see depicted in this picture on the right. So here on the upper side of the image, you see the inference part, the procedure. So you say that you have an embedding representing the task that you want to solve. And so based on a particular scaling function, you then apply through this gate, you create essentially this mask, attention mask, that would somehow bring the representation forward as modeled by this attention. So you essentially bring it to the next layer based on this idea of attention to that, with that particular notion of a task. You're saying to focus on particular neurons or activations instead of others to really bring the task home to solve that particular task. And so what's interesting about these strategies is that it does not start really from necessarily from a pre-trained model as the previous approach. It can be all essentially learned So you can also learn these embeddings and the tension mask, everything. And they also propose a quite of an interesting idea to transform all of these from let's say an attention mask that is soft, in a sense that you can train with back propagation, to something that is more hard, and you can regulate this hardness based on a particular parameter. And then this idea that you have some form of forward transfer based on cumulative attention. So you are saying that there's a better explanation maybe in the paper, but essentially you're saying that things that were important to attain to for the previous task should be maintained also to the next tasks you encounter. And I think this is quite an interesting trade-off in terms of accuracy and effectiveness. And you may read the official, let's say, the original paper if you want to understand more the relationship also with piggyback, which is plentifully discussed into the paper itself. Okay, final last approach that I wanted to discuss in terms of approaches, architectural approaches, a couple of examples that would help you understand what are the main ideas around this category is again a paper involving masks, that is super masks in superimposition. So this paper triggered quite an interesting discussion into the continual learning community, especially gliding the importance of backward and forward transfer. As in this case, the main idea is to use the notion of, well, based on the ideas of the lottery ticket hypothesis. I don't know if you're familiar with it, but essentially you may find, even on a randomly initialized network, you may find a particular mask. I think also in this case binary, but I'm not sure, that would be able to solve in a proficient way the current task, that is model the particular data distribution, the current experience, just by tweaking this mask and not the weights themselves. So that's quite powerful, because in a sense, you may also have an efficient strategy where you do not maintain even the main weights into the memory, and you can generate them on the fly based on a particular seed, a random seed, right? So, and you generate them, and you just train this particular supermask, and then you save all these supermasks related to that particular task. That is quite, as we know, contained in terms of memory. And so that will be quite interesting for even edge devices. And then the interesting aspect of this paper is that you can also, this mask is so small that you can actually superimpose it with the others. And in the paper, they also proposed, superimpose, I mean that all these different masks can, let's say, be used somehow concurrently, even in the inference step. And there is a procedure indicated in the paper to select a few of those that would help you solve a particular task. So this is quite interesting because it poses some interesting questions in continual learning about this idea of the necessity of having like complex, robust representations learn over time. Right? So we are saying that we are able to solve complex tasks even without learning those representations, but just the masks. And also this idea that randomness may be itself a source of powerful representation for learning in general. So this is not new, especially for the reservoir computing guys and researchers. But I think that it also poses an interesting question, and hopefully sparking interesting in the connection between randomness, learning, and continual learning. So that's quite interesting, and we also are starting to do this here in Pisa. If you're interested, we are working with key players like Claudio Gallicchi, who has worked a lot in reservoir computing and eco-state networks, and how we can use them for continual learning as well. Okay, so just as a summary, then we can take a quick break, I guess. the architectural methods may be quite effective in terms of performance metrics. I think the few methods that can guarantee you even zero forgetting, if that's what really concerns you, and may be quite effective, especially where we have the availability of different task supervised signals. You have a reasonable amount of tasks that you can model over time, and they are quite robust even in terms of hyperparameterization. There is also an interesting link here with structural plasticity in biological learning systems. So we know that the brain and from recent neuroscience discoveries that the brain is employing different strategies for learning continually, not just regularizers in various forms, a bit of replay that is happening at some levels somehow. We know from different signals that are bring back and forth from different parts of the brain that this may be happening, and but also in terms of structural plasticity, we know for sure that new synapses are grown every day, every hour, and every second. So that should gives us an heads up with respect to this idea of indeed the investigating architectural strategy, how they would interplay with other approaches like regularization and replay ones. And this is also why we're going to discuss in the next lecture about hybrid approaches. I think they are quite powerful, not only in terms of practical applications they can solve and flexibility, but also finding say new approaches that would not only be also more biologically inspired, but also able to overcome the actual limitations of these different set of approaches, as they are mostly orthogonal somehow, as we know also from the free lunch theorem and other approaches in machine learning. Sometimes using different strategies and models may be quite effective. Yes, and more flexible and dynamic architecture rearrangements is something that I think will be very interesting for future research in this area, where these approaches are quite rusty. I mean, difficult to make a bit more flexible and generally applicable. They really are, as many strategies in continual learning, they're really focused on specific definitions of the continual learning stream of data. Okay, so I think we can stop here, have a quick break, 5 minutes break, and then we can get your eventual questions, and we can move to see how these algorithms are implemented into Avalanche. Okay, welcome back to the second part of the lecture. I guess we are gonna just look very quickly over the different implementations of a couple of strategies that we discussed today in Avalanche, just to refresh you the idea of the plugin system in Avalanche and how you can implement a custom strategy based on those, let's say, plugins, and develop even your own plugin to create a new strategy. And then I will just show you how you can start to play around with a possible assignment, trying, let's say, different regularization strategies that we have in Avalanche, for example, to solve a class incremental task. You see, it's quite difficult, and as you grow in terms of number of experiences you encounter over time, that's really difficult to generalize with the strategies, at least that we discussed so far, like LWF, learning without forgetting, AWC, elastic way consolidation. And I invite you really to play out with these so that you may understand also how tricky it is to parameterize those solutions. And so let's look very quickly now at different implementations in Avalanche, at least these three strategies, as an example. Okay, so sorry, within Avalanche, you can find the different strategies implemented or directly as different strategy inheriting from the base strategy. So there are a couple of those like ICAR, DeepS LDA, cumulative, and etc. R1. But then most of the strategies are implemented as plugins. So again, plugins are better in terms of implementing strategies in Avalanche, because then this would help other people to plug this particular plugin into their own strategy and make the whole problem of continual learning kind of a compositional one. So for example, AWC is implemented as a plugin so that, as we have seen in the previous lectures, you can plug it and play with the orthogonal strategies like the replay one. So you can use replay and DWC together and to maximize possibly the trade-off, accuracy and efficiency trade-off. Okay, now I use the trick that Andrea suggested. And so that we have a bit more flexibility, even though I don't know if this is a bug or what, but so if I click here, for example, okay, now it opens another tab, but then if I click here, it does not anymore. Double click, okay. Okay, so that was me. Perfect. Then, okay, so we're gonna see maybe quickly AWC, LWF, and the CWR star. And maybe you can start from this, as we already discussed that this is a quite of a say simple architectural yet effective architectural strategy that you can use directly in Avalanche, and you can also use as a reference for implementing your own approaches and maybe find different variations that would work better in your specific scenario. So here, CWR star plugin is implemented just as a subclass of the strategy plugin, so the let's say parent class for defining a particular plugin in Avalanche that defines all the different callbacks, if you recall, that defines the train and evaluation loop. So with CWR, that again is mostly based to architectural changes that are operated when you start training and when you end. So before starting and after the end of the training, the step for the initialization and a step for the consolidation into the consolidated memory, then we need to just implement these as two different callbacks here. So the whole strategy here is implemented as just this different specification of the two callbacks after training X and before training X. X stands for experience. So maybe you can start from before training. So the before training approach is exactly what we would expect. So we compute the number of examples per class we encounter in this particular batch of data. With this function, examples per class, starting from the data taken from the actual data set, no, the attribute from the current experience. And then we compute then for each class, essentially the number of times we have encountered those. And so based on the notion, we reset essentially the weights. If you recall, put all the weights at 0 we have not encountered so far, and then apply instead from the consolidated memory the weights that we already learned and plug them into the actual temporal memory. And then we have for the after training X, the consolidate step. So we take from the temporal memory after training what you learned so far, and we consolidate it back into consolidated memory. And then we set the consolidated weights for inference usage, for example. So this memory of the consolidated weights, when we want to do inference and test the system, should be applied to the actual current model that is representing our mapping function. And then, of course, we don't have the time to go through this, but you have the implementation of the consolidation step, really following the nomenclature and definition of the pseudocode we have seen before. So there's no really difference here. And so you can look at different code, but as you can see, it has like very few lines of code describing the different operations that we would need in these two different callbacks. But you see why we believe that the plugin system is fundamental in Avalanche, and you can see why just by looking at these different functions. So you can just specify two methods in how much 10 different lines of code, and you get a clear picture of the main strategy that you're trying to develop. It's different from a naive approach. So this is powerful because you can just write a single Python script. As you can see, it's less than 120 lines of code total, and that would represent your strategy, and that would be easy for other people to understand. instead of finding all the tricks and tips that you have hidden into your code base, as we often had to do when we were looking and exploring different strategies in continual learning in the early days, right? In different codes that were not even PyTorch, I don't know, someone working in Caffe, someone working in C++, someone else working in NumPy. And so you see why having a shared code base may be useful for everyone in this research area. And so not only enforcing compositionality and reusability, but also easy to understand features and making sure that anyone can prototype a new strategy very fast. And again, this will be the only thing that you will need in Avalanche to start experimenting, because you need to implement your own plugin, and then everything else is already there. So from the data loading to the evaluation and metrics and so on and so forth. So that's quite a jump from starting from scratch and developing everything you need for an experiment. I guess all of you started as PhDs as without this kind of tools at hand, and you know how much effort goes into this when you want to do an experiment. So maybe we can look at LWF very quickly, because we can use it in the note we're going to see next, and then I let you guys explore all these different plugins that we have implemented here ready for you. So the LWF plugin, again, is implemented as just 100 lines of code. It's even easier. As you may recall, it's just a distillation step based on a distillation loss. And I think the only thing that you need, well, in this case, it's the opposite ordering. So we have a couple of specific functions that we may use. This penalty function and, sorry, if I go up and down, and the distillation loss. So you may define a distillation loss simply as, in this case, a KL divergence, but you can use also more, let's say, easier losses and would work fine. Between the logits computed at the step before, so we set these targets that we can compute from the model, starting from the latest step on the current data, and the actual, what is this log? Okay, it's the opposite. Okay, it's the actual log is and the output from the previous from the previous output, and you can essentially make sure that these do not diverge too much. So that was the main idea, right? And this would define the basic distillation loss. The penalty instead, in this case, is a bit more articulated, because in this case, we try to model both implementations. So when you have a multi-add model and when you have a single add, that essentially is somehow changing over time in a sense, because you have a few classes that you have seen in the previous maybe experiences, and instead neurons or classes that you encounter in the current one. So you may want to operate the distillation only in a subset of those overall units that you have in the final single add implementation. And this is exactly doing this. So if you look at, we loop over eventually to the different tasks, different adds, and we operate using this distillation loss for each of those adds, or we just do the distillation step on a single add, just considering a portion of these units for the distillation. And then LWF is just implemented as just the specialization of two different callbacks, the before backward and after training X callback. So the before backward, guess what, is the callback that is called right before the backward pass. So after you have defined the loss, the current loss, and you want to add some penalty, right? So in this case, this is just computing. Well, we decide what kind of hyperparameter we want based on maybe some policy. We decide we compute the penalty based on the function we defined before, and then we add this penalty to the loss, and that's it. We add the regularization term as we would expect. And then after training experience, what we need to do is to just prepare for the next iteration. So we save a copy of the model after each experience and update the previously classes encountered, as this would be needed when we want to operate a distillation step of the appropriate number of classes and maybe partial units that we have seen only before. actually, if you implement this from scratch, so without considering these different implementations, like LWF is implemented with just, I don't know, 10 lines of code. It's quite easy and maybe simplified even more. But already this more complex and comprehensive solution, you see, it's quite understandable, and you can really go through each line of code that is, not so fancy, and understand how it is implemented at home. So here I also started a draft notebook. Maybe we can also upload all the different notebooks, and they are on each page of the course lecture. Because as for now, you may find the recording, the slides, interactive slides that you can operate directly on the website, and also the PDFs of the slides. Maybe what would be useful would be links to these particular notebooks we have seen in class, or let's say something you can download. But well, here let's start by clearing out the output, and so. After a simple installation, pip install command of Avalanche, the bleeding edge version. And by the way, I can anticipate to you all that the 16th of this month, so actually before the finish of this course, it's going to finish 20, we're going to have, let's say, an Avalanche Dev Day, 16th of December, in which we will launch the official beta of the software. So if you're interested, you're all invited to participate. It will be a totally free event, and I expect you all to participate so that we can discuss together what are the main issues of the tool. If you see maybe some interesting features that you may want to add, and your suggestion will be very, very welcome. And so let's have a bit of fun on the 16th. We're going to be here actually in the department the whole day. So in case you're interested also in participating in person, that would be very much appreciated. And we can discuss about relevant, algorithms, approaches, everything related to continual learning and the course, as we have discussed so far. But I will send you a notice via email as soon as we have a draft program available. Well, okay, that took a while. So Avalanche has been installed. And just to finish this lecture, I just wanted to start drafting this notebook in which it can be like a skeleton for you to try that homework at home. So in using different strategies in Avalanche and plugins, and see how, for example, a regularization approach or architectural approach, they work in different settings we have discussed so far. So I really invite you to put your hands into Avalanche right now, after we have discussed essentially all the aspects and modules of Avalanche, and start playing with it, at least at this, let's say, user high level, let's say abstract approach to it. And so this would mean, for example, just starting with the classic benchmarks like the split and list, creating as always the benchmark instance, and then, so in this case would be just 2 experiences based on split and list. So you have 2 different experiences. For the first one, you have 5 different classes you want to distinguish, and then for the second one, you have the other 5 of the 10 total classes you have in MNIST. So sorry, so this is a wrong attribute name, so it's not permuted and list, but it's split and list. Then if you get access to the specific streams and you instantiate the optimizer criterion as always, then what you can do is to start by instantiating a naive approach and see how that would go, right? In this simple application of Avalanche for this benchmark. And recall, let's say a basic instantiation and evaluation protocol has been already defaulted into the evaluator parameter of each strategy within the base strategy. So you have that by default. But if you want to tune, add different metrics, you can always instantiate an evaluation plugin and pass it to the evaluator attribute of every strategy and get a more detailed, let's say explanation to the strategy of which metrics you want to monitor, which loggers you want to use. Okay, So in this case, we are looking for the different accuracy metrics at different levels. So we may say we are interested in the mini batch layer, let's say granularity, epoch granularity, experience granularity, or stream granularity. In this case, just the first two, just for convenience, so to see how the model is performing on each of the different experiences and overall. And so you can see here that after the training, oops. In terms of experience, let's say accuracy, after the training on the first experience, you have a 96% accuracy, and then you're not really able to do any kind of forward transfer if you're not trained on the second experience. So in that case, the accuracy is 0. And so if you use a naive approach, after the learning a second experience, you got a massive amount of forgetting. You're able to solve the new task, but not able to maintain the knowledge preserved on the previous task. Then if you have the same exact script in which you just add okay, here in the naive strategies, just add the LWF plugin that we have seen right now, right, as implemented in 120 lines of code. This would not magically trigger the internals of Avalanche so that we are able, without specifying anything. Yes. So without any kind of hyperparameter selection here, we probably get an interesting result. So let's see how it goes. If the magic of Avalanche will take place, or we totally screwed this up. So now the training is progressing, and so we get what we would expect, right? So the first step in time, we get good performance on the current task experience, and then 0 on the second one. We have not seen any data from that yet. So now let's see how it goes, enforcing that regularization, that distillation on the knowledge we have learned in the previous experience, in the previous task. And this would give us, teach a lesson either way. So in a sense, you should always try to fine tune your hyperparameters and not try to apply directly what's encoded into Avalanche. But in this case, as you can see, Avalanche played this magic, and you don't need to specify any hyperparameter, and you get a nice preservation of the knowledge of the previous task, thanks to Andrea and his tweaking magic in the basic implementation at AWF. And so in case you're wondering what are different parameters for a particular strategy, a different scenario, you may want to check the official papers and what the authors say about these strategies. But then you have also, for some of the strategies already implemented in Avalanche, the possibility to look for reproducible CL, repository that Andrea put together, and essentially is is maintaining, where we have an assessment, in this case with respect to the latest bleeding edge version of Avalanche, of many of the strategies we have in place for the beta release, so that you can be sure that given a set of hyperparameters, you're able to replicate the results of the official papers implementation. So that's cool. Many of these strategies have been assessed that way, and you can find the different hyperparameters directly within the strategies directory. So if you go to, for example, WC experiments, then you see that, for example, for permuted MNIST, you get all the different hyperparameters that would guarantee you, more or less, to achieve the same performance as was proposed in the official original paper. So I think this is quite of an important endeavor as well. So as we progress with the development of Avalanche, we're also interested in guaranteeing the fact that this is a solid bench, a solid code base that we can actually use to improve reproducibility as well. And we are going to progress in that direction, and And sorry if you find some art patches in the tool and some strategies are not really being validated, but that's a working process as we are doing our best to provide that. So thank you so much again for your attention. Do you have some questions before closing the lecture? No, but remotely here, no. So thank you so much for your attention, and I'll see you again next Monday.